I'm Emma Kate Matthews, an architect and a composer, and I'm interested in poetic and practical resonances between sonic and spatial worlds. So I've developed a practice that I call spatiosonics, which cultivates ways of thinking and making that sit between things like architecture and music, but also the practical and the poetic, the material and the immaterial, and the felt and the heard, and so on. And as part of this practice, I compose and perform works for architectural spaces with distinct acoustic opinions, such as the Sagrada Família. And in this work, I'm treating architecture as an active collaborator rather than just a neutral container for sound. So alongside these site-responsive compositions that I make, I also make instruments as part of a series that I call Resonant Bodies. And the resonant bodies are a family of tuning fork and bell-like idiophones that make a number of thresholds, both audible and physically tangible. So particularly those thresholds between hearing and feeling, and pitch and pulse, and musical sound and noise. And I developed these instruments through a combination of things like computational simulation, digital fabrication, and compositional experimentation. So they emerge from an unusual but very productive overlap between architectural, engineering, and compositional workflows. And as well as making sound, they also act as apparatus for tuning ideas. So they help me to calibrate compositional and spatial desires against the realities and resistances of physical spaces and material. So therefore, they're translating abstract sonic relationships into tangible and physically accessible forms. So in this sense, they operate a little bit like physical mathematical models in relation to the abstract line equations that describe their topologies. I think of them as apparatus through which relationships and thresholds, again, between things like space and sound and feeling and hearing and pulse and tone, can be explored and tested and also negotiated. So many of the same questions that emerge in architecture, therefore, remain active within these pieces. So that the questions of material behavior, structural performance, types of resonance, spatial response, and relationships between sounding bodies, listening bodies, and the environments that they inhabit. And because many of the works are eventually performed within these sort of acoustically opinionated architectural spaces, the acoustic behaviors of the instrument and the space that they inhabit unavoidably interact with each other and have a conversation. So the bodies therefore operate as a sort of miniature architectural ecology situated within a larger and more complex spatial and acoustic one. And it's partly for this reason that the methods used to develop these works borrow so heavily from architectural and engineering workflows. And the process of designing and building them relies heavily on tools like parametric 3D modeling and modal frequency simulation. So in architecture and engineering, these tools are typically used to identify and predict and eliminate or suppress resonance in buildings and other engineered structures, because mechanical resonance is generally understood as something that can make structures uncomfortable to inhabit, or in more extreme cases, structurally unstable and dangerous. However, in my work, these same tools are redirected towards the cultivation of resonance. So rather than designing vibration out of objects, I'm using modal frequency analysis to design how mechanically resonant behaviors emerge through aspects relating to geometry, material properties, and the distribution of mass and thickness. And then sonic characteristics such as timbre, they're more difficult to predict using this process, but it's relatively straightforward to anticipate things like the fundamental pitches that the pieces will produce when they're hit or excited in some way. So when coupled with parametric modeling tools and evolutionary solvers, the digital model becomes a sort of rehearsal space in which resonant behaviors, geometries, and material relationships can be iteratively explored and negotiated before being committed to any physical form. And traditional bell casting often involves repeated cycles of melting, lathing, or tuning, and even recasting in order to refine the tonal behavior. And this can be both energy intensive and also time consuming. But through digital simulation, although it's never fully predictive, a large amount of this iterative design work can take place before any metal is cast or machined. And the fabrication processes used in this work also draw heavily on architectural manufacturing methods. So techniques including 3D printing are used to produce positives for highly complex and extremely thin, doubly curved shell geometries, alongside other techniques like metal laser sintering processes, where fine metal powders are fused layer by layer using a laser to form these surfaces and these volumes. So these digital models allow resonant behaviors to be explored and refined before the objects physically exist. And in some cases, I also use ray-traced acoustic simulations and impulse responses to anticipate how the bodies might eventually interact with the architectural environments that they're performing within. And as is often the case in architectural production, the digital model functions as a tool for developing the eventual object rather than providing a perfect visual representation of it as an alternative. But discrepancies inevitably emerge between the simulated model and the real fabricated result. So this happens dimensionally, geometrically, and also sonically in the way that the bodies resonate and produce sound. And to understand these discrepancies, I 3D scan the finished pieces and compare them to the fabricated geometries against the original digital models. And I also acoustically record the pieces, and I use frequency analysis and spectrograms to visualize things like the overtone structures that they emit alongside the predicted model behaviors in the modal frequency analysis. So tiny inconsistencies in things like the density, the cooling, the machining, and the surface finishing and the surface qualities introduce subtle variations in pitch and resonance and timbre that can't really be fully predicted in advance with the digital model. And importantly, these deviations are not seen as problems to be eliminated, but they're treated as important moments in which the material begins to participate in shaping the spatial and sonic behavior of the work in its own right. So these variations fundamentally shape how resonance eventually emerges once the bodies enter and interact with architectural space and start to perform. And the title, Resonant Bodies, it's fairly literal, and it speaks to the fact that different forms of resonance emerge through the design and fabrication and performance and spatial interaction of these bodies. So these resonances are, of course, mechanical and sonic, but they're also architectural and poetic and cross-disciplinary. And they arise relationally through interactions between materials, vibration, space, and listening bodies. Sonically, the bodies are intentionally designed to produce multiple tones simultaneously, so they're polyphonic, and they deliberately explore dissonant interval relationships, so particularly the minor second and minor ninth. And I chose these intervals because their frequency relationships generate dense spectral interactions and unstable interference between neighboring partials and overtones. And as physicist Hermann Helmholtz once observed, intervals like the minor second and minor ninth are perceived as especially rough. So he gave this description, a sort of material metaphor, but they're perceived as rough because their partials don't align through simple whole number frequency relationships. So they produce these fluctuating interference patterns between neighboring overtones. And these unstable interactions generate audible beating patterns or rhythmic oscillations that are produced through alternating constructive and destructive interference between closely spaced frequencies. So rather than aiming for tonal purity or harmonic stability, the resonant bodies are intentionally cultivating these unstable and shifting conditions. So again, it's allowing resonance to evolve dynamically in time and space. And it's something that is not demonstrated didactically, but it's allowed to emerge. And that's the really important distinction in all of the work that I make within the umbrella of spatiosonics. And as a result, the sound they produced is never entirely fixed or singular. So the tones are continually interfering, reinforcing each other, dissolving, re-emerging, and changing as the bodies are interacting with their architectural hosts and their surroundings, and the listening bodies and each other when they're played simultaneously. So again, the resonance therefore becomes contingent and relational, and it's something that emerges intermittently. It's not a reliable or constant thing. So these slight unpredictabilities that are introduced through making them physical by casting and machining and these other digital fabrication processes further intensifies this potential for harmonically noisy behaviors. So these small deviations in geometry and thickness and surface quality are creating additional layers of instability and interference and subtly altering pitch and overtone structure and timbre. And as a result, the final sonic character of each body is emerging through the material opinions and tendencies that they embody, and these resistances once they're sort of activated in performance. And although these works operate at the scale of musical instruments rather than buildings, they embody a wider ecology of architectural knowledge. So the mechanical, disciplinary, and poetic resonances that I mentioned that they engage they're never entirely fixed or stable, but they only fully emerge once the bodies enter performance mode. So they have to be activated in order to sort of give their knowledge to others and make that knowledge accessible. And despite the care and precision that goes into their design and fabrication, their sonic behavior is continually reconfigured by the architectural environments that they're performed within, especially the ones that are particularly acoustically opinionated, as I would say. So aspects such as acoustic reflection and interference and absorption, spatial positioning, and even the movement of listeners within a space all begin to alter how this work is experienced and understood. And again, it's not reliable or consistent. Architectural space, therefore, becomes more than just a backdrop or a container for sound. It's actively performing in collaboration with these instruments and shaping how different forms of resonance are allowed to propagate and become perceptible mechanically and otherwise. And owing to the unstable and contingent behavior of the bodies, these performances are never entirely repeatable or, again, fixed. So concepts of resonance are transient and continually negotiated between materials and spaces, and also technologies and manufacturing processes. And this is perhaps where the project sits most clearly between architecture and music, through an understanding of both as practices concerned with organizing relationships between bodies, materials, space, time, and sensation, rather than treating the other as a metaphor. And I do have some sound samples of how these bodies can behave in action.